Alright, pre-calculus kiddos, well, welcome back to another edition of me teaching solving trig equations from home. Hopefully we finished the first two videos now, and today we're on ST3, which means we're solving trig equations. So a lot of what we've been learning now is finally kind of gearing up to this stuff, where we're going to start solving trig equations. In order to get there, into some of our actual problems, I want to explain conceptually kind of what's going on. In order to do that, what I'm going to have us do today is we're going to consider. So hopefully at home you're going to consider. Remember, okay. So don't forget, it's still me. Okay, so consider. Okay. We're going to consider the equation y equals sine of x. Now we've graphed y equals sine of x before, and so when we graph y equals sine of x, it should look. I'm trying to do a better graph here. This is pretty important. It should look something kind of like this. We're going to scale every 2 lines is worth pi. And so then 2 more lines is 2 pi. And 3 pi. And maybe 4 pi. And remember, sine goes all the way up to +1, all the way down to -1. And so when we graph sine back then, I'm going to do it in maybe blue here. Remember, sine had a period of 2 pi. That's the cycle it took to complete. Halfway between 0 and 2 pi across its midline at pi, and at pi over 2 the y value was 1, and at 3 pi over 2 it's -1. And so this was our graph of sine, right? And we established this graph of sine from our unit circle, evaluating different values, and eventually we got here. Now this graph of sine repeated forever. It's a periodic function, so it repeated forever in each direction. We're going to show maybe one more period in this direction, maybe about here and about here. Okay? And so we should have something like that. Yeah? Okay? And so this is our graph y equals sine of x. Now, if I say, okay, I want to consider when this graph is equal to, when this graph sine of x is equal to 1/2. Okay? Essentially, I want to know where this is true. Now, you may think back on your unit circle, trying to figure out where sine is 1/2. That's where the y value is 1/2. So at like radical 3 over 2 comma 1/2, you may say, oh, Mr. Jensen, I know that sine of pi over 6 is equal to 1/2. And so what happens is a lot of students look at this problem and go, Mr. Jensen, I know this one. X has to be pi over 6. And I go, great, that's one solution. But remember, that's also going to be true over here at this location, which is at 5 pi over 6. Because at 5 pi over 6, the coordinate is negative radical 3 over 2, comma, positive 1/2. And so you go, okay, great, so it's pi over 6 and 5 pi over 6. And you think maybe we only have 2 answers. But if you understand graphically what we're doing, graphically what we're saying is if we look at when this equation, sine of x equals 1/2, it's essentially when it crosses this dotted line. Well, it crosses this dotted line here at this spot here, which we said is pi over 6, but it also crosses it here at 5 pi over 6. Okay? And so we got our 2 answers. However, if you look on the graph, graphically we can see that it's also true that this equation, y equals sine of x, is equal to 1/2, not just at these 2 spots, but it's also equal to 1/2 at these 2 spots. And if you want to figure out where these 2 spots are, you'll notice because the sine graph takes a total of 2 pi to repeat, that after 2 pi, every solution of it is just 2 pi further away from it. Meaning, this solution here of pi over 6 has a similar solution here. And this solution is 2 pi away from pi over 6. Now to figure out that value, we would have to take pi over 6, and we'd have to add 2 pi to that. Now if we got a common denominator, that would be pi over 6. This is like 2 pi over 1, we multiply by 6 over 6. And that would be 12 pi over 6. Or we can add those and get 13 pi over 6. So this solution here is 13 pi over 6. Right there. And you'll notice that's exactly 2 pi away from pi over 6. To find this solution here, this solution of 5 pi over 6 is 2 pi away here, over here, when we take 5 pi over 6 and add 2 pi out to it, again, we'd get a common denominator, and that would be 5 pi over 6. This is like 2 pi over 1. We multiply this by 6 over 6, and we get 12 pi over 6. And so we would get 17 pi over 6. And so now we have a solution at 13 pi over 6 and a solution at 17 pi over 6. And so now we have 4 answers for when does sine of x equal 1/2. Now the problem is that we know we know the equation y equals sine of x doesn't stop after 2 pi, it doesn't stop after 4 pi, that this goes on forever. And so if you understand this graph goes on forever, it's going to cross this line, y equals 1/2, infinite times, which means we have infinite solutions. And so as we get into solving these problems, we're going to have to be able to write out infinite solutions. Now, there's no way that I'm going to write out infinite numbers because we can't ever do that. So what we're going to do is find the pattern of how often those solutions repeat, and we're going to write that pattern. We saw here that these solutions repeated every 2 pi. So if these solutions repeat every 2 pi, then we're going to say, hey, we're just going to add multiples of 2 pi, and we're going to talk about how we do that. Okay? So take this as like a precursor, kind of like understanding big picture what's going on, why we're going to have infinite solutions as we get into some of our trig equations today, and then you'll get into some of your trig equations for homework this week. Okay? So let me erase this here, and we're going to work through our first example. The first example is the one we were just doing, I believe. Number 1. We want to, let me see. We want to solve, and we want to find all solutions. This is important because eventually our instructions are going to change in future lessons, okay? So we want to find out when does sine of x equal 1/2. Okay? So what we need to do then is think where on the unit circle, because that's essentially one period for the sine graph. Where on the unit circle, where during its first initial period, does sine of x equal 1/2? And we would say that is true when x is equal to pi over 6 and when x is equal to 5 pi over 6. Notice here, x doesn't refer to an x or y coordinate on our graph. X is referring to the angle on our unit circle, okay? So at the angle of pi over 6, if I did sine of pi over 6 using the left-hand rule, sine is the y value at pi over 6, which is 1/2, okay? And at 5 pi over 6, the y value at 5 pi over 6 is also 1/2. But we said we have infinite solutions, okay? We have infinite solutions. So if we have infinite solutions, not just one solution or 2 solutions or even the 4 that we found, we need to say how often do these solutions come up? Well, because of the graph that I showed before, the solutions come up every time the period repeats. Okay? Well, for sine, the period is 2 pi. So every 2 pi, we get a new set of solutions. A new set. Which I can't write. A new set of solutions. Which is to say, if we were to take this and we were going to find our next set of solutions, what we would do then is we would add 2 pi to this, okay? But then every 2 pi, so I need to add multiple sets of 2 pi. I don't want to add 2 pi one time. I want to add 2 pi like infinite times. So what I do then is I say I want x to be pi over 6 plus, we write this as 2 pi, but I want multiples of 2 pi, so I write this as 2 pi n. But I don't like how 2 pi n looks, so most people write it as 2n pi in the future, okay? But you can do 2 pi n, this is fine. And if we do this, this says that I get a solution at pi over 6 plus 2 pi n but I introduced a new variable. What does n mean? N is going to be here n is part of, n is an integer. N is an integer. An integer, just remember that means like, that's the counting numbers, forward and backward, positive and negative. So like -3, -2, -1, 0, 1, 2, 3, and going on forever. Okay, that's what an integer means. Now, I don't want to have to write n as an integer every time I introduce n. And because mathematicians are lazy, we want to find easier ways to write what we have to communicate. And so one of those ways to do that is we say n is an element of, and this weird alien looking E in math means element of, means a part of the set of integers. And the set of integers has like a weird letter. Well, the way we use it is it's a capital Z with an extra bar going down on the side. And so this means that n is an integer. So on your homework and in your notes and when you're doing these problems, you can write every time you write the letter n, write n as an integer. Or you could just write this, n is an element of the integers. Now when we do that, here we got x is equal to pi over 6 plus 2 pi n, and I said now that n is an element of the integers. Here's what that means. That this generates for me an infinite list of solutions for when n is all kinds of numbers. N can be any integer, -3, -2, -1, 0, 1, 2, right? So let's just look at a few different cases, okay? And normally we won't have to look at all these cases, but I want to kind of prove that this gives us our list of solutions. Notice if n equals 0, then x would equal pi over 6 plus 2 pi, and n would be 0. And 2 pi times 0 would be just 0, and that would just be pi over 6. Right? And so this is one of the solutions we knew was true from here, or from kind of my intro that I gave you guys. But let's say that n was a different number. Let's say, what if n was, if n equals 1, then this would be, x would equal pi over 6 plus 2 pi times 1. And we did this when we take pi over 6 and we add essentially 2 pi to this. We already got a common denominator in the intro, and we said that this was equal to 13 pi over 6. And so you'll notice this is going to produce another answer, 13 pi over 6. Our next answer down the line, if we follow that sine curve, would be when n is equal to 2. And we would be adding 2 to 2 pi times 2, which means we'd be adding 4 pi, and we'd get another answer. If we let n equal negative numbers, then we'd get answers on the other side of the y-axis there. And so we would get infinite answers in both directions. So generally speaking, when they say find all solutions, we don't need to show all these different solutions unless we're just bored at home and we don't know what to do during the whole coronavirus stuff. So if you're bored, go ahead and find me infinite answers. But most of you guys aren't that bored, or maybe you're bored, but not bored enough to be finding infinite solutions. So when they find all solutions, we write this, pi over 6 plus 2 pi n, and that will give us our infinite list for the pi over 6 sequence. Notice, this doesn't give me the list of answers generated by 5 pi over 6. So for 5 pi over 6, I have to write the same notation. Then I'm going to write 5 pi over 6 plus, a lot of times, like I said, I don't like writing 2 pi n. I like to write it as 2n pi. Potato, potato, however you want to say it. This is how I prefer writing it, and so this is how I will usually write it. Most textbooks tend to agree with me, or more likely I agree with more textbooks. And so this then produces 2 sets of infinite answers, but these are all the solutions. I'm confident these are all the solutions based off of me looking at the graph. And also, I know that's the only time that sine of x is equal to 1/2 in my 1 unit circle, my 1 period. And after that, my graph just repeats. So hopefully, we understand how to find all solutions for when sine of x equals 1/2. And then our goal today is to do a few more problems kind of like this. Okay, so hopefully we're following along and we're ready to try our second example. Again, the instructions here are still to find all solutions, which will be your instructions for all of your homework problems this week. Okay, here, if I need to find all solutions here for 2 cosine of x plus radical 3 equals 0, this is the problem we're trying to solve. What I need to do is I need to get cosine of x all by itself. I'm trying to isolate that term. So we would treat this like 2x plus radical 3 equals 0. So we would subtract this term over. When I do that, I get 2 cosine of x equals negative radical 3. Then to get cosine by itself, it's being multiplied by 2. So I'm going to divide both sides by 2. And I get cosine of x is equal to negative radical 3 divided by 2. And now here, I've got cosine isolated. And so now that cosine's isolated, I need to stop and think, where on the unit circle does cosine equal negative radical 3 over 2? Meaning what angles, x is representing an angle, what angles is this true? And this comes down to our unit circle knowledge. Remember, cosine is our x value, and our x value is negative in quadrants 2 and 3, and negative radical 3 over 2 at these 2 spots. That's true here at 5 pi over 6 and at 7 pi over 6. So that's negative radical 3 over 2 here, comma 1/2, and negative radical 3 over 2, comma negative 1/2. So cosine then would give me these 2 answers. And again, because cosine is like sine, cosine graph goes on forever, means that we're going to have, again, infinite solutions. So here's how we write this, okay? I'm going to write it over here just for, I don't know, space, and I want to write it over here. That I can say that x is equal to 5 pi over 6. And then below that, I'm going to write x is equal to 7 pi over 6. But those are only 2 of my answers. I want to say I want the infinite set of answers. And I know the next set of answers on the cosine graph. Remember, the next set of answers on the cosine graph. So we got, what do we get? Like 5 pi over 6 and 7 pi over 6. Maybe like, maybe here and here or something. I know the next set of answers here are going to come 2 pi later. Remember, they're going to keep going on forever, this way and forever that way. And so what we do then is we say, oh, I want these answers plus all the answers that are 2 pi away from this, and we write this as, again, 2n pi. This will generate a list of infinite answers here, and we'll write 2n pi, generating a list of infinite answers here. And then we need to say, we introduce n. We say, what does n represent? N represents an integer, some sort of number, okay? And so if I want to say n is an integer, I'm lazy, and as I explained earlier, I'm just going to write it like this, where n is an element of the integers. And I'm just going to write this, n, it almost looks like NEZ, but the E is a weird symbol for element in mathematics, and the Z means the set of integers. And there we go. I don't have to write anything more. I don't have to go find all those infinite solutions. I just need like the original ones on the unit circle, and then I write 2n pi, which will give me the infinite set, and I'm able to solve problem number 2. Okay, hopefully at home you're tracking with me, and we only have 2 more examples to do, and hopefully then you'll be set and ready to do your homework. On these next 2 examples, here's what we're doing for this next one. We have 5 sine of theta plus 1 equals 3 sine of theta. So notice now, the equations are going to start quickly looking more and more complicated. However, it'll help at first if you treat your trig functions, like in this case sine of theta, or if we see cosine of theta, or eventually we're going to see tangent of theta. If you treat them like x's at first, it may help you think of a way that we can solve it. In this case, if you saw 5 sine of theta plus 1 equals 3 sine of theta, you may go, I don't know how to do that, Mr. Jensen, that's crazy. And I go, yeah, that may seem a little weird, but if I tell you this, I say, hey, well, think about it this way. I want you to think about, what if I gave you a problem like this, where I said, I have 5x plus 1 equals 3x. Could you solve that? And most of you guys would go, oh yeah, I could do that, no problem. I would subtract 3x from both sides, and I would get 2x plus 1 equals 0. I would subtract this one over here, 2x equals negative 1. I would divide by 2, and I would get x equals negative 1/2. See? And I go, this problem is exactly the difference. Exactly the difference. This problem is exactly the same. And so in the same way, we're going to try to get all of our signs on one side and all of the numbers on the other side. I like to have positive coefficients, so that's why I'm kind of bent to subtract 3 sine of theta over from both sides. 3 sine of theta from both sides. And when I do that, 5 sine of theta minus 3 sine of theta is 2 sine of theta plus 1 equals 0. And so we're able to kind of add and subtract them to both sides. We're not working with trig identities, or we're verifying them where we couldn't work on both sides. We're solving trig equations. In solving trig equations, we can move stuff to either side as long as we follow all of the mathematical properties that we've already established to be true. Now I'll subtract the 1 over, and I get 2 sine of theta is equal to 1. And then I would divide by, equal to negative 1, almost. Divide by 2, and I get sine of theta is equal to negative 1/2 here. And so now, again, I play the game. I've got here, and now I need to use my good trig knowledge. When does theta, sine of an angle, in this case theta, equal negative 1/2? That's when the y-coordinates on my unit circle are negative 1/2. Well, the y-coordinates are negative 1/2 at the pi over 6's, but down here in quadrants 3 and 4. So that's going to be when, again, I'm going to write it over here just for space. That's going to be when theta equals 7 pi over 6. And that's when theta equals 11 pi over 6. And again, the instructions for these problems was to find all solutions. So this is only 2 of the solutions, but the sine graph repeats forever, which means we have infinite solutions. And the way that we show that is we say, so there's another solution at every 2n pi for both of these. Every 2n pi we get another set of solutions over and over and over again. And again, we need to say, I introduced n, and every problem that I introduce the letter n, I need to tell my reader, hey, I know what n means. Mr. Jensen, n is an element of the integers. And if you don't like that, you can write it in words. You could write n is an element of the integers, but I'm too lazy, and most of you guys, even if you don't understand it, you're lazy enough that you'll write this as well. This is problem number 3, and we're going to fly into problem number 4, and we're going to call it a day. Here we go. So problem number 4, I'll erase here. And let's see what problem number 4 has in store for us. Problem number 4, 3 tangent of x. 3 tangent of x minus 3 equals, what did I say? Make sure it's not that. Equals negative 6. Okay. So again, the problem's starting to look a little more complicated. We have now tangents involved, and tangent brings a whole new ball game in here. And we have to we have numbers. So the first part is try to isolate your trig function here. In this case, it's tangent of x. And so we're going to do that by first adding 3 over to take care of this, and then we'll divide by this 3. So when I do that, I get 3 tangent of x. When I add 3 over here, negative 6 plus 3 is negative 3. And notice what I did here, I'll show it, is we added 3 to both sides. That's how we got this. And then I'm going to divide both sides by 3 because this 3 is multiplying the tangent of x. And when I do that, I get tangent of x equals negative 1. And so now we need to stop and think, when does tangent of an angle, x represents an angle, when does tangent of an angle equal negative 1? And so now we have to use that unit circle stuff. But tangent means, remember, tangent is y divided by x. And so we got to figure that out. Because it's a little complicated and I need this, I'm going to show a graph of tangent. If you remember what y equals tangent of x looks like, that at every pi over 2, on the parent function we had asymptotes. And up at 1 and down at negative 1 here, we had a point and our graph looked kind of like this. Maybe I can graph it in blue. And so this is what our tangent graph looked like. Now when we graph tangent graph, one of the things that we noticed is that the period was shorter. That for sine and cosine, the period was 2 pi, meaning it took 2 pi distance for our graph to repeat. But for our tangent graph, you'll remember that this period, the total length it takes to repeat, is just pi distance. That's very important because when we go to solve something like this, we then will have to kind of edit our infinite solutions part because you'll notice the graph is just going to continue to repeat over and over and over every pi distance. Here and here. And we want to know, when does tangent of x equal -1? Well, tangent of x equals -1 on our original one right here. And that spot is at -pi/4. So we would say, okay, that's when x is equal to -pi/4. But nowhere else on the tangent graph does it equal -pi/4 in just one period distance. And instead it equals -1 here and here and here. And because tangent's period is just pi, I don't have to find any other solutions on the unit circle. I can just say, I know that's going to be, that's to say x is equal to -pi/4 plus, instead of 2n pi, because my period's not 2 pi, I can just write plus n pi, where n is an element of the integers. And when I do this, this will generate a list for me of infinite answers. This will give me -pi/4, and then I'm adding just 1 pi, or multiples of 1 pi, adding or subtracting it, to find my other answers. It's possible that you may have approached this problem slightly differently, and if you did, you could probably still be okay. So if you understand it the way that I did it here, then hopefully we just, I don't want you to tell you to stop the video, but you could stop the video because then you're good. However, if some of you are thinking, but Mr. Jensen, you wanted me to find all the solutions on the unit circle where tangent of some angle is equal to -1. And when I did that, I got x is equal to 3pi/4, and I got x is equal to 7pi/4. Because both at 3pi/4 and at 7pi/4, that the coordinates would be radical 2/2 and negative radical 2/2, or vice versa. And when you divided them, you would get -1. And you go, Mr. Jensen, I didn't see the problem like this. I went from here and I got these two answers here and here. And I go, great. Notice two things. One, these answers are both correct and part of our infinite solutions. 3pi/4 would be this answer right here. This is where 3pi/4 is. And 7pi/4 is coming down the line. 7pi/4 would be right here. And so on our graph, it's also going to be true there. So you found more of our infinite solutions, and you say, is it okay if I write this? And I go, absolutely, sure. If we write this, we still have to show that we're having infinite solutions. So either you can then understand tangent's period is pi, and write plus n pi for both of them, which is kind of silly because then you're writing two sets of the same answer. You're telling me like the answer's 5 and the answer's also 5. And so usually we don't do that in math. It's not mathematically incorrect. It's just kind of a waste of our time. So you could write plus 2n pi for each of them. And if you write plus 2n pi with n an element of the integers, for each of them, this will generate the complete set of answers. Or you could just write plus n pi for one of them, and you don't even have to write the other one at all. You can just write x equals 3pi/4 plus n pi, and this will generate the same set of solutions that this did. And so both of those answers would be fully correct. Hopefully this has made a lot of sense to you and that you're getting it. If not, then you can feel free to shoot me an email to say, Mr. Jensen, you didn't explain that very well. Or in our weekly huddle, I'm going to see you guys on Thursday this week. In our weekly huddle, you guys can ask me some questions about it. Other than that, I hope you guys are having a great day. Stay on it, pre-calc kids. I know that times right now are just not necessarily the most fun, and trying to stay motivated to take notes and do math and keep up with your classes and stuff. But Titans, you guys got this, okay? So keep it up. I'll see you guys soon.